Thanks for the introduction. And before actually starting to talk about screaming channels, when electromagnetic side channels meet radio transceivers, I want to do a big shout out to all the wonderful people which make this work possible. It was by no means by me alone, namely Giovanni Cumarati, Sebastian Pöblau, Tom Hayes, and Aurelien Francillon, which all joined in this project to make it happen. So let's jump right in. What are screaming channels? I try to give you the great idea in one single slide. So our nowadays life is more and more reliant on like all kind of smart embedded devices, oftentimes with radio frequency components in them. For instance, like this summer I lived in a flat which had a smart lock. Like I didn't get a key to the flat, no, there was this weird lock and I had to download an app with a phone to open it, and yeah, that was just a thingy. So this is not black magic at all. In the end, on those smart locks, there's just a small, tiny microchip which does some computation. It has some digital logic, some memory, and a radio, which will, over Bluetooth, communicate with the phone. Maybe, internally, at some point in time, it's doing some kind of encryptions, for instance, AES, to like validate that I'm in fact the user who is allowed to be there. And those kind of things make digital noise, like small noise, which is there, which just comes from the different computations. This is all known so far. And now what screaming channels is basically that we figured out more or less that those little digital noise leaks over in the analog radio part, gets mixed into the signal and transmitted over the air as a side effect. So what we could do, we could hook up on the other side with a laptop, a software-defined radio, some equipment, and analyze what's going on, and at the end of the day, with some black magic, get the secret cryptographic key. And I really want to stress here, this is not what I did on the smart lock at my flat. It's just a like logical scheme about screaming channels, the coarse-grained idea. So that's not the full talk. I want to tell you a little bit the story of it, like how we got there, what was the idea, how discovered we the leak, how we implemented the attack, and so forth. So let's start with a little bit of background, which we need. So one thing, obviously, as we're dealing with radio frequency like transmissions, we need to have a little bit background on those. So one very common concept is modulation. Let's assume we have our wave here, which are some information we want to share. So we will have a carrier frequency at a different speed and mix those together to, in the end, get like the information signal modulated over the carrier. Like this is basic amplitude modulation. We will see a little bit of this later in the talk. Another way to see this is in the spectrograph, in the power spectrum. So we have like the carrier frequency in the middle, like the huge spike, and the actual information signals on the sidebands of those signals. Now, side channel attacks, the next background topic. So it is known that like even if you have provable secure cryptography, at the end of the day, it has to run on some real hardware, like some real chips. And real chips are not perfect. They make some noise. And if this noise is based on the intermediate computations, then they may also leak in this noise the intermediate data. And attackers can observe those leaks and try to reconstruct the cryptographic secrets being computed. One specific class of side channel attacks are electromagnetic side channels. So this is still nothing new. Like basically digital logic is like consumed current or different currents when it's like switching, and those variations of current change the electromagnetic field around the processor. And this is very similar to power side channels and has been exploited in the past. There has been, for instance, one attack on, or have been attacks on smart card, like one work we want to refer here is Casper et al. This is really like close proximity. You really go close to the card. Then on farther distance, like cryptographic running on a laptop by Genkind and all, like in the initial paper it was like 15 centimeter, by now there are results up to 1 meter, and a full different set of electromagnetic side channels, which are not dealing with cryptography, is for instance Tempest, where you would from like a far distance, measure the electromagnetic emanations, and could reconstruct more or less what's going on an old computer screen. So how do we actually carry out those conventional side channel attacks? We have our smart card, which has some physical activity and consumes some power and some current in the end. We go very close to it with some probes, measure what's going on, and the clock, like the leaks get modulated over the clock, which is a carrier in that sense, and we can extract traces. One device which does this, or which is very popular for performing those kinds of attacks, is the chip whisperer, here shown to the right for you, just to give you a coarse-grained idea. So once we have those traces, we can run different kind of attacks on those traces. For instance, like simple power analysis attacks, correlation power analysis, or template power analysis. The same works for electromagnetic attacks as well, as those are very close coupled and tied together. Now, the last part of the background, mixed signal chips. So the idea of mixed signal chips, what we saw already in the first slide, is to combine the digital logic with the analog radio part or analog parts on one die. So that's why mixed signal, so digital and analog part at the same time. And the idea is, when you have it on a single chip, that you can reduce the costs, like the full complex system you want to build gets cheaper, and you can save also power. And it's very like convenient for developers because you just have one chip, maybe one API to drive both the radio and the digital logic at the same time. So that's pretty neat. And there are like tons of examples of devices using mixed signal chips. Like, for instance, I would say a lot of phones have those things in their Bluetooth transceivers or baseband. It's like small Wi-Fi dongles. Those kind of things use mixed signal chips under the hood. However, as we already saw a little bit before, digital logic produces noise. And this noise can propagate easily to the radio, to the analog parts, which is also pretty well known to the designers. And the designer of those chips try to keep the noise as low as possible in the sense that they want to have the chip working and functioning. However, they don't care about secrecy in this case. So we were wondering, what if the digital noise which leaks over contains sensitive information, like cryptographic informations from cryptographic operations. And with this intuition, we started our investigation. However, there are a lot of different factors to consider. Like, on which frequency should we listen when we try to measure this? What kind of implementation of crypto should we look like? Should we look at hardware implementations, at software implementations? What kind of antennas would we need to use? What kind of chip or protocol in the first place? Should we look at Bluetooth chips, at Wi-Fi chips? Where will the leak be? Will it be in the amplitude, in the radio? What would be the proper distance? So all of this are just a lot of different factors we had to consider. And there were really months of trying around and not getting anywhere in the first place. And we tried different chips, multiple chips. We wrote in the end some custom firmware which could enable us measurements. And one day we actually accidentally tuned on the wrong frequency. Like, we were normally listening on the main channel of Bluetooth because we analyzed the Bluetooth chip. And one day we just got by accident to some offset, and we saw a leak dependent on the operations. And this is something I want to show you, and I brought you. So if you were wondering what this small black box here is for, that's more or less a replication of our lab setup, which fell a little bit apart, but it's not a big deal. So what do we have here once it's reconstructed? Here on the side, this is just some USB switch, which is like switchable, like we can power off the USB devices here via command line from our PC. This is just convenient and nothing related to our attack. Here, this is a little small Bluetooth chip, a Bluetooth device, which could transmit over Bluetooth. And here on the far right, we have a software-defined radio, a HackRF, which is in the lower end of, or the lower cost end of software-defined radios. So I recorded this demo, but I thought after lunch, let's have a little bit of thrill, let's do a live demo out of it. And what could go possibly wrong here? So here we have a small GNU radio plot. It's rather simple. We basically just have something to drive the HackRF and show a FFT plot and a waterfall plot. So let's start the full thingy. Takes a little while, and here we have it. Send it over to another window. And so here we have it. Here we have the frequency, which we measure over 5 megahertz bandwidth over time to the left. And the more green something is, the stronger the signal is there. Here on the right, we connect to the Bluetooth device, which runs our custom firmware. So if we press help, we have all the help of our firmware. And the first thing we do is we start emitting a continuous wave. So as we see, suddenly a lot of stuff is here happening in the spectrum. So this is basically just the Bluetooth device transmitting a continuous wave, not any data, just purely sending. We already see here some green lines on the right, which are dependent on our data. But what got really interesting, if we now do another operations, so currently the firmware itself is just in a scanf loop, like it's waiting for us to give input. So let's do some input, and we see, while we do some like loopy operations down here, a change in the spectrum. And this was the moment when we got pretty excited, because we found a leak over the radio, over the air, depending on what we were doing on the device. So this is all fine and good. Let's stop this for now. We were excited, we had a leak, but we didn't really understand it in the first place. So we took a more experimental and then really like structured approach to figure out what was going on. So we took our mixed signal chip, and this time we just didn't put just a software-defined radio next to it, but a spectrum analyzer, which would basically show us not just a 5 megahertz spectrum, but a wider spectrum over the full range. And in the firmware itself, we had 2 different operations. Basically, we could do some operations which slowly loops and some operation which are looping fast. And we see this here to the right in the spectrogram, or the schematic of a spectrogram. We can see the slow loops at a different frequency as the fast loops. And also, what is nice to see here is a difference between conventional and screaming side channels. Because in the conventional setting, like where you will go really close to the device, you have the leaks at 64 megahertz, which is basically the clock speed of the processor. So there, the clock of the processor acts as carrier, while here we have the same behavior at some sidebands of the radio chip. So this is basically a very nice observation for us. And based on that, let's figure out what happens here exactly. Like how does this come to existence? So on a logical level, we could say that we have some digital noise which gets modulated by the clock, and then later on gets mixed with the Bluetooth carrier and sent out over the radio. How does the digital noise come into existence in the first place? So, as stated before, the chip does, based on the operations, has a different current consumption. Let's, for instance, assume, like just as example, a NOT gate here, which would switch the input value from 0 to 1 and from 1 to 0. And if you want to do the switch between from 0 to 1, we would have to fill some parasitic capacitance on the circuit. So this you can basically imagine as like some kind of reservoir. It has to be filled before the switch is fully done. However, and based on that, we consume a certain amount of current. However, now, if we want to switch back from 1 to 0, we would have a lower currency needed to do that, because of the parasitic capacitance is full and flows also back to ground. And this is the way basically the small EM leaks started to exist. Then later on it gets mixed on the clock signal or clock carrier as used as in like conventional side channels or electromagnetic side channels. This could either be in a direct manner, like where some actual U signal, or by non-linear components in the die. Then, on the screaming channel side, we have this propagation from the analog noise, which we have now on the clock carrier, which we could measure from really close, to the radio. So how does it actually propagate? We have multiple theories how this could happen. One theory is due to substrate coupling, like based on the fact that both digital and analog logic is on the same die, there's some coupling based on the operations in the digital part coupling over to the analog part. Another idea is that they are on the same power supply, so it leaks over the power supply. So we consume some power in the digital part, and as a result, there is some jitter in the analog part. And afterwards, how does this get mixed into the Bluetooth carrier? So also here, we are not completely certain and just have multiple theories. Like here we have like a small circuit of the radio output, we have a voltage controlled oscillator, we have a digital to analog converter and a power amplifier. And one idea is that the noise leaks over into the voltage controlled oscillator or the power amplifier or like some other means which we don't know yet and have to investigate more. So this is basically the full idea how this happens. And to sum up these explanations, there are three parts to the screening channels. Like first is the generation of the noise, then the propagation from the analog, from the digital to the analog domain, and then the transmission over the radio. And yeah, once again, here's really the difference. Like the generation itself is conventional electromagnetic side channel tags, and the screening channels abuse the propagation to the analog domain and the transmission over the air. Now, knowing all of this, how could we build an attack? We implemented a proof of concept attack to recover some secret key of some AES computation running on some custom firmware we wrote. So this firmware would basically all the time just doing encryptions and at the same time transmitting Bluetooth packets, like random Bluetooth packets and encryptions at the same time about something else, like totally not related to all, but just happening at the same time as we wanted to build a proof of concept. So if we now look again at the waterfall, so this is again a waterfall plot as we saw before, just with changed axis. So now we have the time on the x-axis and the frequency on the y-axis. And the more yellow it is, the stronger the signal is here in this waterfall plot. So if the radio is off, we just see some noise. We don't see anything really happen. If we put the radio on and start transmitting Bluetooth packets, we see some activity happening. And now, last but least, if we start AES encryptions, we suddenly see like a lot of different jitter and a lot of different changes going on. So what we else can see here is first the wait loop. Like we already saw the loop before in the spectrogram, where we just waited for scanf. It was in a loop. It were some like frequencies emitted at some certain, with a certain power at some certain frequencies. And another interesting thing we see are the different Bluetooth packets. Like once the Bluetooth packet is sent, we have a hole basically in the waterfall plot because the radio is not sending anymore anything. And when AES is running, we actually see a lot of things going on. And if we will start, so we see the beginning, and if we will start demodulating it, we suddenly would get something like that. And I mean, it's not very obvious if you're not used to it, but we were staring at those things for like months. And in the end, if we saw something like this, it's like, oh, this is obviously AES. Like you see this 10 power spikes there. This is like the 10 rounds of AES. Isn't that awesome? So this is more or less how we obtained traces. We did some additional things for cleaning the traces and getting nice things out of it, and then we'll start an attack against the collected traces in a second phase. So this is another demo, this time less risky, pre-recorded. So we would run our attack script, specify the data path, where we started in the individual trace and how many traces we want to use and which kind of attack. It took some while to load all the traces, and now it's running the attack. So this is a correlation attack, where we basically have like a power model of the AES running, and we will try, or like at a specific point in the algorithm. In our case, it was the output of the S box in the first round of AES. So we have a model for this, and we'll test now every byte for this model of the key individually, and we'll get like which has the highest correlation to our model, we will assume as the right byte. And as we see here, after a while cycle, this was a real-time recording, we will have our best key guess, and as this is like a controlled environment, an experiment, a proof of concept, we also know the real key, and as we see, it's matching. So we extracted magically over the air the secret key of the AES computation. So that being said, our attack scripts involves like the extraction of clean traces. It involves some basic attacks which we based on the implementations by the chip whisperer. It basically comes with a correlation attack and a template attack. And we attack two different AES implementations running on the chip in the proof of concept. Namely Embed TLS, which is running on a lot of different devices. It was formerly known as Polar SSL, and Tiny AES, which is a very small implementation of AES trimmed for size and efficiency. Important, all of this is open source, like you can look it up on GitHub and try to do it at home. The link for it will be shown later. So, how did we evolve the attack? Like, I now showed you that it is working, but what are actually the distances we are talking about? In the very, very beginning, when we built the attack, we just hooked to the chip via a cable. Like we soldered on the antenna some cable to be able to directly attach to it to get very good traces. And then we slowly started to scale up. Like, can we go to 15 centimeter like in like traditional electromagnetic side channel attacks? Yes, we could. Could we go to 2 meter? Like this is actually at home, so we needed some space. And 2 meter also perfectly worked fine. Then we kind of ran out of space in our flat. So we changed, and luckily the guys from the Air 2 lab of India jumped in and offered us to use their anechoic chamber, where we could like improve it even more to 3 meter. To 5 meter, and as we see now, the antenna also gets a little bit more, how to say, dedicated. It's basically still just a normal Wi-Fi antenna, just a directed one. So it's like a TP-Link 80 euro equipment here. And last but not least, which was very exciting for us, was getting the attack working to 10 meter. So just to let this sink in, attacks which were before in a distance from maybe 1 meter possible are suddenly now possible over a 10 meter distance. Okay, knowing all this, how could we protect against screaming channels attack? Because attacking is one thing. On the other hand, you know, it would be nice to mitigate things like that in the future. One common countermeasure would be like classic protections as they are already employed in other cases, like masking or noise in the cryptographic computations. However, this, in our opinion, will just lead to a classic arms race. Because if you do masking, we can apply some higher level side channel attacks to break this and so forth. Another option would be to go for software specific countermeasures. Like, let's say, when we do cryptographic operations, we just don't transmit anymore. Problem solved. Absolutely, unfortunately not very practical, because you would need to switch the radio on and off a lot. Sometimes you cannot switch it off while you do cryptographic operations, like imagine, for instance, link layer encryption. You don't want to put off the radio while you encrypt your packets. Another thing would be to turn off the channel completely, which is a little bit senseless, because then you don't have radio at all. So what would be like probably the best countermeasure is hardware specific, that in the design process, during the design process of the chip, that we would already like try to prevent those kind of attacks. One big question here is, will it increase the cost too much? Like it would be very costly and the chips would get more expensive, which is basically like leading to mixed signal chip a little bit being ad absurdum, because you know, we want to have them cheap to use them in a lot of different devices, but at the same time, if we now suddenly hardening it on the design level, it gets more expensive. Just another example of a mixed signal chip would, by the way, be this small presenter. So all of that being said, let's come to like the last part of the talk, the final remarks. We responsibly disclosed our findings to multiple vendors and multiple certs, and then they acknowledged this is a general problem, good work, we will look into it. 2 specific vendors are tried to replicate our results in their own labs, and 1 vendor was actively looking together with us into short-term and long-term countermeasures against this. Another big thing, or like another big critique, which could be applicable here is, okay, nice work, interesting, but what we did was just a proof of concept, right? So what's the big deal about it? We are not breaking actually like some Wi-Fi over the air. So our intuition is that attacks in a more realistic setups will follow. Like if you look in the history of side channel attacks, the first couple of side channel attacks also had the same problem that people were saying, oh, that is not a realistic setting, it doesn't help. By now, actually, at least against timing side channels, oftentimes implementations are hardened by design. So we really think that there's a possibility for more realistic attacks in the future. And while we implemented just a very, very simple attack, we think that we can do much better because on the, we really went very naively into it. Like our collection mechanism is very naive. You could, for instance, instead of just using 1 radio, put multiple radios at different spots to make the collections faster, more efficient, get a cleaner signal. You could do the actual signal processing we do more efficient because also here we are like just very naive approaches which we took. And we could also app using specific protocol weaknesses. Like if we could force a protocol to encrypt certain stuff, we could combine this knowledge with our attack. And another big intuition between like showing this proof of concept to you and to the vendors is that if we show it early, we can like start working on mitigation faster and we don't need to wait until we have like a full website with logo and so on. And to conclude the talk, all of this is a general problem, the screaming channels, as soon the sensitive processing is close to a wireless transmitting source. You could, for instance, also look at other kind of shits, at hardware AES or at Wi-Fi. And it's also not really just limited to integrated circuits. So as a result, this is like, in our opinion, a new point in the threat model space if you design those chips, because now electromagnetic attacks are possible from a distance, which was not before. There were actually, for instance, posts on the ARM forum where people were specifically asking about mitigations and implementation about, against power side channels. And the official answer was, as those kind of side channels require physical access, we don't consider it in our threat model, because if you have physical access to our chip, you have way bigger worries than side channel attacks. But now, with going up to 10-meter distance, it suddenly changes the game a little bit. And yeah, all of that being said, we think we're just at the beginning, we're still working on it, and I guess more of it will follow in the future. That's it for now. As I see, I was kind of fast. Let's go to the bonus slide. So you remember I was saying that it's not limited to integrated circuits, right? That was just 2 slides ago. So if we look at this document, this is from the original Tempest documents, which was a program by the NSA in the 80s, where they tried to, well, basically methods of spying. For instance, the attack on the where you would reconstruct the screen of a PC from remote by measuring the electromagnetic emanations. So, reading this document, there is stated in the beginning, there are 4 basic means by which compromising emanations may be propagated. They are electromagnetic radiation, conductions, modulation of an intended signal, and acoustics. So, as we see, we have here the electromagnetic radiations in the top, the different conductions as point B and C, and at point E we have the acoustics, and then the point D, where like following the logical scheme of this document and would be written modulation of intended signal, which is more or less what we did, we just have 6 lines redacted. So we don't think that this is like specific on mixed signal chips, because back in the days they were not there, but in general the idea kinda was around, I would say, but just probably not meant to be public yet. And with that, now finally we do the real thank you slide. You can find the code online at this URL and more information on our website about the attack, which is more an informative page than a panic page. And if you have any questions, you can ask them now or send me a mail or reach out on Twitter. And yeah, thanks.
Okay, thank you. Do you have questions?
Yeah, thanks for the talk. What's the signal strength of the side channel compared to the intended signal in terms of decibels? And the background of the question is, how cheap an RTL or SDR hardware could it use to actually detect the side channel?
Okay, so the first part of the question is how is like the ratio of the side channel signal to the intended signal. We don't made any concrete measure of this because we found the side channel noise on a different channel than the main signal. So the main signal was not interfering, and hence we were not really comparing those different powers. And the second question about our equipment. So for finding the basic leaks which we had, we actually used things like the HackRF. Then later on in the advanced attack over 10 meters, we used the USRP.
Thank you for the talk, very interesting. Did you characterize the difference of leakage between a hardware implementation of the AES and a software one?
Yes, we tried both. Like what we attacked in the proof of concept are the software implementations of AES, but at the same time we also run some attacks against there it is. We run some attacks against hardware AES as well, or some tests. And I thought it's harder because the hardware AES leaks less, and this is a faster clock speed, so we would need higher gained equipment. And in the initial experiment which we run, we were nevertheless able to recover 4 bytes out of 16 from simple AES hardware implementations. So we think that with some advanced techniques, hardware AES may be breakable as well.
Thank you.
You mentioned that you came on the frequency where you saw the manifestation of the modulation was by accident. Subsequently, did you develop a technique to understand how to get to that frequency in a more sort of deterministic way?
This is an excellent question, and as it turns out, the frequency we got by accident was basically just the main Bluetooth frequency on which we were emitted, offsetted by harmonics of the clock. So there was a combination of the clock signal as carrier with the actual Bluetooth signal as carrier.
Just a small technical question. I'm not sure I understood when you mentioned the different all distances you could reach, and you said after 2 meters your flat was not large enough, but then you moved to an anechoic chamber. So can you do 3 meters without suppressing the reflections if you have a bigger flat, or is it really just at some point you really need to have a cleaner signal?
So we were focusing on developing the proof of concept rather than doing a full study about the channel, how it propagates, and how we can deal with noise in the background. So that being said, what we saw, it's possible out of 10 meters in a noisy environment, and obviously we would have to apply some more noise correction if we go farther in a noisy environment, but we didn't explore this direction yet. And the anechoic chamber was in that sense really good because, well, on the one side there was more space, on the other side it gave a better test environment to understand all of this.
Okay. Do you have more questions? No, I don't see. Okay.
Do you think these attacks can work with other types of modulation? Say frequency modulation or things like that?
I have to think about this for a second. So the question was whether those attacks work also with different kind of modulation. Yeah. In general, I would so there are different things in modulation, right? There's the modulation of the actual intended signal, and then the way of how the unintended or like our side channel signal gets modulated.
I mean the intended.
What? I
mean the intended modulation.
So the intended modulation, I think, shouldn't be that big of a problem. It just changes a little bit how we would need to apply our signal processing.
And a very stupid one. Did you try to brute force directly the first signal on 64 MHz on the second or fourth Nyquist zone to have the direct signal and to avoid to make IQ demodulation and so on?
Yes, the thing is, a signal on the direct traditional frequencies, the 64 megahertz, appears really fast from the spectrum. It's, I think, in our measurements, after 10, 15, 30 centimeters, we could not really see it and distinguish it from noise anymore.
Even with more than
130 I have to say I'm not the expert on the kind of amplifiers we use and how strong we amplified the signal, but I think over this really fast gets interleaved with just noise and we cannot pick it up anymore.
Okay.
There's
one more question.
Yes, I would like to know if you need to know in advance which frequency you need to scan, or.
And which frequency for our specific example, it's basically the main frequency of the intended channel offsetted by the clock harmonics. We have a formula for that in our paper. However, we assume there may also be other frequencies or other settings how the signal could leak, which could be at yet different frequencies, which we just didn't have looked into.
Because sometimes when designing radio-based sensor network, people use frequency hopping, namely both emitter and the receiver agrees on jumping from one frequency to another. And was it possible countermeasure for this
is also an excellent question, because Bluetooth itself also normally uses frequency hopping. And for our proof of concept, we disabled it to make our lives easier. However, in the end, you could work around it by either taking more measurements or by following the hopping sequence with your radio, if you're fast enough, or by just putting very dumb one radio for each frequency and correlating the results. So it's basically just, it makes life harder, but it's not a problem which is unsolved or can be not solvable.
Thank you.
Thank you for the talk. I'm a big newbie when it comes to side channel, so I would just like to understand the context of your work. So did you didn't use any new side channel or cryptographic techniques, but you just adapted the existing ones to new chips which are mixed signal chips. Is this right? Or
yeah, this is a perfect valid summary. We didn't develop new new side channel techniques itself, in the sense of the underlying technique, how you would attack or get the cryptographic secret out of your traces. We basically just found and showed how you can get traces out of a large distance. And with this knowledge now, we think that we could use this to actually develop new actual side channel techniques, because we have a kind of we saw a little bit different behavior than in traditional side channel.
Okay. Thank you very much.
All right. So no more questions? Good. Well, thank you very much.
You're welcome.